Hi and welcome to the second of three videos, and I'm not sure if in the first video I told you there was three, but this is the second of three videos for section 2.5. So in the first video we were looking at horizontal and vertical shifts. In this one we're going to start by looking at reflecting our graphs. So reflecting makes you think of what? It's the mirror image. So depending on where we have, so we're going to be dealing with a negative sign. Depending where that negative sign is, it's either going to reflect it on the x-axis or on the y-axis. We have the following. So to graph y equals minus f of x. So it's on the outside of the function now. So we might have, if we're graphing negative x squared, then that, we're going to reflect it on the x-axis. And when we do some examples, you'll kind of see inside, outside, reflect on the x, reflect on the y. Just giving it to you verbally here for now. So to graph y equals f of minus x, so now the negative sign is on the inside, we're going to reflect on the y-axis. So, a couple examples. Switch pens here for you guys. So let's say I want to graph f of x equals negative x squared. So as I mentioned up above. Well, my function is the x squared function. The negative sign is outside of that. So because it's outside, I reflect on the x-axis. So normally, the graph of x squared would be what? It would be a parabola pointing up. But because I have this minus sign, I reflect it on the x-axis. So think of it like a hinge. The hinge is on the x-axis. I'm going to reflect it. So whatever's up on top now goes down below. So you actually end up with a graph that's an upside down parabola. So negative sign is outside. Graph the basic function, or maybe plot it out with dotted lines, and then reflect it on the x-axis. What if I want to graph f of x is equal to square root of minus x? So here's one where I have the base function, the square root, but the negative is inside the function. Because it's inside, that's what this notation means, I reflect it on the y-axis. So my normal square root of x graph would look like what? It's that rocket, or the fireworks headed off to the right. But because I'm reflecting on the y, again, think of it like a hinge or a mirror. On the y-axis, it flips to the other side. So take all of this, move it over to this side, so you actually get a graph that looks like fireworks or a rocket going off to the left side. So that's our reflection. Just simply on the x or the y-axis, depending where the negative sign is. What if I have vertical, well, now we're going to look at stretching or shrinking. First, vertical. So vertical stretching or shrinking. So again, let me put this in words here. So to graph y equals some constant c times the function, we have two options. If c is greater than 1, then we stretch it. So we stretch y equals f of x vertically by a factor of c. And again, we'll look at a couple examples. And second, if c is between 0 and 1, so if it's a fraction, we shrink, or what I like to think of this instead, if you want to say squish. So if I have a parabola is what? X squared. So if I have 1/2 times x squared, well, 1/2 is a fraction. That's what this notation means here, basically. So if it's a fraction in front of the function, I shrink it vertically or I squish it vertically. I push the whole thing down. Instead of making it a thin cup, it's like a bowl. So I'm going to shrink it or I'm going to squish it vertically by a factor of c. So again, let's look at a couple examples. And again, if you're not caught up writing, just go ahead and hit pause, catch up with the writing, come on back. So first example, if I have f of x equals 3x squared. So what this is doing is it's stretching the graph. So instead of, if I just have x squared, if x was normally 1, y would be 1. But now, if x is 1, what's y? It's 3. So it's essentially like someone grabs the end of the parabola and pulls it up by a factor of 3. So when you sketch it, it might not look that much different, but instead of the normal parabola looking like this, 3x squared is going to be skinnier because it's growing 3 times as fast. And similarly, if I have f of x is equal to 1/2 x squared, well now, instead of the normal parabola, looking like so, it squishes it or it gets pushed down so that it's only growing half as fast. So it's going to look something like that. So now, let's combine everything we know so far. So what do we know? We know vertical and horizontal shifting. We know reflecting. We know shrinking or stretching. So let's say we want to graph. I'm going to start saying sketch because it's not exactly to scale, so it's just a sketch. But f of x is equal to 1 minus 2 times x minus 3 squared. All right, so we got a lot going on here, right? So let's kind of keep tabs of what we have. So first of all, our base function is what? It's x squared. Like, get rid of everything else and just look at the variable and what's happening to it. So it's an x squared. It's a parabola. This minus 3, and so we're always going to work from the inside out. So inside the parentheses, we have the minus 3. So inside, horizontal, opposite, I hop. So that means what? It means we're moving to the right 3 units. If I start moving away from here, oh, I hit a 2. So that means what? The 2 means I double it, or I'm going to stretch it. So it's going to be a little bit skinnier parabola. Uh-oh, minus sign. So that means what? The minus sign means I'm going to reflect it, but am I reflecting it on the x or on the y-axis? Well, the negative sign is what? It's outside of the function, so that means outside is my x-axis. So reflect on the x-axis. And then lastly, I have the 1. So that means what? This means my vertical shift. So that's up 1 unit. So let's try to do this. And so as you're doing this on an exam, homework, maybe you can keep track, but you just use dotted lines or use like a different colored pencil so that at the end, because you might have a bunch of stuff going on here, you want to be sure that you're pointing out what the final product looks like. All right, so we have x squared, that's our parabola. I moved to the right 3 units, so 1, 2, 3, so that puts me over here. So maybe erase as you move along so you know what's left. Then the 2 doubles it, so now it becomes a skinny parabola. Then I reflect on the x-axis. So the vertice is still at the point 3, 0, but what happens? It gets reflected down. So it gets reflected down as a skinny parabola. And then lastly, I move up 1 unit. So I have a parabola that's pointing downward. I have to slide its vertice up 1 unit. So that puts me right here, which is at what point? 3, 1. And then it's a skinny parabola from that point. So you can see why I put sketch and not graph, because it's just a rough idea. It's a parabola that's skinny, pointing downward with its vertice at 3, 1. So there you go. You didn't have to plot points. You didn't have to, I don't know, go to some other measures. You were basically able to use the transformation information that you had to this point. So we looked at the vertical stretching or shrinking. We'll also talk a little bit about the horizontal, but we're not going to deal with it much here. If you're going on to Math 127, you're going to be dealing with sine and cosine curves, and there you will be doing horizontal and vertical stretching. In this class, we won't be dealing with it too much, but you still kind of need to know what's going on in terms of the operation. So horizontal, stretching, and shrinking. So, and you can see I left most of this. Why? Because we're only going to get a few changes here. So, we're going to graph y is equal to f. So just as before, the vertical was outside. So if we're talking vertical shift, it's outside the function. If we're talking about horizontal shrinking or stretching, it's now going to be f of c times x. Our constant is inside. So actually, let me erase this because there's a few changes, so I might as well rewrite it so we get them all straight. So to graph y is equal to f of some constant times the function inside, we have the following. If c is greater than 1, we shrink. So again, it's inside, so it's opposite of what happens. So we shrink or we squish the base function horizontally by a factor of 1 over c. So when we were vertically stretching it, the number was on the outside. If it was bigger than 1, it stretched it. If it was smaller than 1, it shrinked it or squished it. And again, if c is a fraction, then we stretch y equals f of x by horizontally by a factor of 1 over c. So I'll show you graphically what this means. Again, it's going to make more sense once you get to Math 127 and you start dealing with sine or cosine curves. But let's say, so here's an intro to Math 127 here for you. Here is a sine curve. And it goes on forever. Negative infinity, positive infinity. If I have, let's say, so let's call this y is equal to some function f of x. So if I have y is equal to f of 2x, so that number's on the inside, it's a positive number, so what happens? I shrink it, I squish it. So this graph will look the same, it's just that now it's going to be, well, something like that. But you can see it squishes it down. Versus if I have y is equal to f of 1/2 x, so it's a fraction on the inside. So instead of squishing it this way, it gets stretched out, so now it looks something like that. So instead of taking this long to make one cycle, it doubles how long it takes. And that's all that happens. But again, we're not going to be doing too much of that here in 126. It's more of a concept once you get to 127. The big thing you guys need to know, the base functions, x squared, x to the third, square root of x, and absolute value of x. And then know your vertical and horizontal shifts, your vertical stretching, and your reflecting. If you know those, you'll be able to tackle any of the graphs you're asked to transform. So come on back, and I'm going to introduce you guys to the even and odd, the concept of even and odd functions.